Okay. Hello Year 12, it's Mrs Horton here. I'm going to do a video for you today on how to construct a Born-Haber cycle. I'm going to do two videos. The first one is on what a Born-Haber cycle is, the processes that it represents, and I'm going to show you how to construct one for a fairly simple potassium chloride salt, so a 1+ and a 1- ion. In the second video, I'm going to take you through how to produce a Born-Haber cycle for a slightly more complex ionic compound, such as aluminium oxide or perhaps potassium oxide, something where you have multiple charges on your cations and anions. So to start with then, Born-Haber cycles, often just abbreviated to a BH cycle, is a way to diagrammatically represent the processes involved in the formation or the dissociation of a giant ionic lattice. So, processes involved first of all are atomization. When we form our ionic compound, we're forming it from, well, not atoms, actually gaseous ions, but before we can turn our atoms into ions, we need to make sure that everything exists as a gaseous atom. So I'm going to stick with the example of potassium chloride, which is in question 3 of worksheet 2. It would actually be a good idea if you had worksheet 2 from your Unit 9 pack. If you had that in front of you as we do this, then you'll be able to see the values and kind of follow along and calculate at the same time. So, first things first then, atomization. With potassium chloride, obviously our metal here is potassium, and in its standard state, potassium exists as a solid. So to atomize potassium, we're going to go from potassium as a solid to potassium as a gas. That's it, okay? For chlorine, chlorine doesn't exist as an atom, it exists as a molecule. So if we want one chlorine atom, bearing in mind it exists as a molecule, we're going to need to put a half there to balance it. Now obviously chlorine is already a gas, it's a gaseous molecule, so we just need to make it a gaseous atom. Okay, so now we've got our gaseous atoms. The next stage is ionization. Now you've encountered ionization before, you've looked at the ionization energy of different metals, and obviously that is the process involved in, or the energy required to remove 1 mole of electrons from 1 mole of gaseous atoms. Well, we've got our gaseous atoms, happy days, let's remove some electrons. So we're going to go from potassium as a gas to potassium as a gaseous ion, and obviously we have lost an electron, no state symbol required, and so you must put that in your equation. But we don't just ionize. Oh, Mr. Parkinson's walked in. Now I'm embarrassed. Do you want to make a quick cameo?
It's not as good as my video yesterday.
Yeah, whatever. It's way better. Right. So we don't just ionize our positive ions, we also form our anions. But this is measured in a slightly different way. So, again, sticking with chlorine as our example, if we have got chlorine gas, that's going to become a negative ion. So it's going to gain the electron that potassium lost. So, our equation is going to look like that. Now, the enthalpy change associated with that is known as the electron affinity of chlorine. If you think about the word affinity, it means, to have an affinity for something is to like it, to be attracted to it. So that is the process by which chlorine is gaining an electron. Now think about what the thermodynamic, or rather thermochemical changes associated with that are going to be. We are losing an electron here, okay? So that's going to be an endothermic process, okay? That's endothermic. To add an electron, to kind of bond form if you like, that's going to be an exothermic exothermic process. Energy is going to be released when we do that. However, that is only the case for the first electron affinity of an atom. Let's take oxygen as an example. Oxygen, as you know, forms an O2- ion, an oxide ion. So if we have, let's say, 2 oxygen atoms, actually for simplicity's sake, let's just stick with 1 for now. The first electron affinity of oxygen will produce an oxide 1- ion, as you would find in peroxides. That is an endothermic process. Sorry, that is an exothermic process. Energy is released. The second electron affinity, taking us from O- to O2-, that is an endothermic process. And that makes sense, because if you think about what you're actually doing, you are adding something negative to something negative. That requires an input of energy to overcome those repulsive forces. So your first electron affinity is exothermic, but every subsequent electron affinity, and you're only going to get to 3-, you're only going to get to the third one, that is endothermic. It requires an input of energy. And you'll need to remember that when you're constructing your Born-Haber cycles. Okay, so let's just go back to chlorine for a minute and assume that we have made our chlorine anion. So now we've got our positive cation, we've got our negative anion. They are going to combine, and that process is the lattice enthalpy of formation. Okay, so we can use a Born-Haber cycle to put all of that information together. So that's what we're going to do now. My board is filthy, so I apologise. It does not work well. Okay.
Oh, sorry, stop interrupting you.
I'm just doing a video.
Yeah, sorry.
Okay, so I'm going to talk you through question 3 on worksheet 2. So make sure you've got it in front of you. So it asks you to construct a Born-Haber cycle for the formation of potassium chloride. Calculate the electron affinity of chlorine. So first thing I'm going to do, I'm going to draw a line, and these lines to create this cycle will actually be given to you in the exam, because you know your ability to draw a straight line is not something they especially want to examine. It wastes time. So first things first then, you need your elements in their standard states. So we've got potassium, which this is a solid, plus chlorine gas as a molecule. Okay. Down here we've got, we've got our salt. Okay, we've got potassium chloride, which is a solid. Now this process here, and the direction of the arrow is important, this process here by which we form our ionic solid from our elements in their standard states, that is the enthalpy of formation. And you've encountered that term before. All of these definitions, by the way, you do need to know the enthalpy change when 1 mole of blah blah blah, and that's in worksheet 1 in lesson 1 of this unit. Okay, so next process then is we're going to try and form our gaseous ions, and to do that we're going to go up and round, and then we're going to come down finally to our ionic solid. So this first process, you remember we said we need to do atomization, ionization, and then lattice enthalpy of formation. So first thing I'm going to do is I'm going to atomize my potassium. So I'm going to go from potassium as a solid to potassium as a gas. Done nothing to the chlorine, that stays exactly the same. Okay? That is an endothermic process, hence the arrow is going up. And I'm just going to put here atomization of potassium. Okay, next thing I'm going to do, I've atomized my potassium. Now I'm going to atomize my chlorine. I'm not doing anything to the potassium, it's exactly the same, but I'm going to a chlorine atom from a chlorine molecule. Okay, so now I've got my gaseous atoms, I'm going to start forming my gaseous ions. First of all, I'm going to do my cation. So I've got potassium atom as a gas, that's going to go to a potassium ion as a gas. I've not done anything to the chlorine, I've lost an electron, and just like you would do if I asked you to give me the equation to show the first ionisation energy of potassium, you would absolutely include an electron in there, and you must do the same here. So plus electron. That's also an endothermic process. Energy is required to do that, and that is first ionisation energy of potassium. Okay, I'm then going to come across here. Now I've got my positive ion, the next process is to produce my anion, my negative ion. And that, as we've already looked at, is an exothermic process. The losing of that, the gaining of that first electron releases energy. So I'm going to do an arrow going down. Chlorine is going to gain that electron, so our equation here is going to look like that. There's going to be no electron in there, it's gone, it's combined with the chlorine atom to form a chloride ion. Okay, so that is the electron affinity of chlorine, and it is exothermic. Finally, we have got our gaseous ions. They are ready to combine and produce our ionic compound, and that is the enthalpy change, that is the lattice enthalpy, sorry. And as you can see, that is also an exothermic process, and that is a highly exothermic process. The size of these arrows, the gap between these levels, gives you an indication of the magnitude of these values, okay? So if you were trying to fill in some blanks, that gives you a bit of a clue. You can stop and do a common sense check. Have I labelled this with a value that's smaller than that? That would mean you were obviously wrong. Okay, so once you've put all of that in, you've got your equations, it's time to put in some values. So again, if you follow along with the worksheet here, then you can annotate your own, if you've constructed one, with the values. So we have got this one here, standard enthalpy of formation of potassium chloride is minus 436. Okay, it's negative, that arrow goes down, so that makes sense. Next one, atomization of potassium is plus 90. Atomization of chlorine is plus 121. And the first ionization energy, where are you? There it is, of potassium is plus 420. We are being asked to calculate this, so I'm going to put a question mark there, and we've been given this, that is a highly exothermic minus 706, and I've not put the units in for all of them, but they are obviously in kilojoules per mole. So now we need to calculate this. There are a couple of ways to do it. The way I do it is this, I just discount this sign here and I add up everything on this side, and I subtract whatever information I have on this side, in this case it's this, and that leaves me with this. So doing that calculation, saying 436 plus 90 plus 121 plus 420 gives you 1067. Subtracting 706 from that leaves you with an electron affinity of 361 kilojoules per mole, and that is an exothermic process, so we need a negative sign. That's how you use a Born-Haber cycle to calculate electron affinity for a 1 plus and 1 minus ion. Next video we will look at aluminium oxide, where you have a 3 plus and a 2 minus ion.